In this video, we're going to begin discussing hyperbolas. The equation for a hyperbola looks pretty similar to the equation for an ellipse. We have 1 on the right side, we have two fractions, we have x minus h squared and y minus k squared for the numerators. The difference is we have subtraction for hyperbolas. So for an ellipse, it was addition between the fractions. And for ellipses, we were adding the terms, so the order of the terms didn't really matter. We always wrote the x one first, but since the order of the terms didn't matter, we designated that A was larger than B. That's not going to be the case here. You'll notice that because now we're subtracting, the order matters, and so we might have the x term first, or we might have the y term first. And so with these equations for hyperbolas, a squared is always going to be the denominator of the first term. And that's going to be the case regardless of whether A or B is larger. So here A is just designating that it's coming from the denominator of the first term. So what does a hyperbola look like? Let's start a sketch here. A hyperbola has two branches, and each one has a point called the vertex. So for this equation on the left, the branches are going to open to the left and to the right. There's one vertex. There's the other vertex. There's a point called the center, which is halfway between the vertices. The line that the vertices and the center all fall on is called the transverse axis. And we have a point inside of each branch called the focus. How close the focus is to the vertex is going to be related to how wide or narrow the branches open. Let's draw our vertical scenario first, and then we'll talk about the values A and B. So if the y term comes first, then the transverse axis is vertical. We still have a center, two vertices, and two foci lying on that transverse axis. The center is halfway between the two vertices, and it's also halfway between the two foci. We'll talk about those distances a little bit more here in a minute. But the branches are going to open up and down now. All right, the distance A, in this first scenario, A is underneath X, so A is a horizontal distance. A is actually the distance from the center to the vertex. And in the second scenario, A is still the distance from the center to a vertex, but now it's a vertical distance since A is underneath the Y term. And then the distance from the center to a focus is a value C, which we don't see in the equation. But we'll talk about where C comes from in a moment. So some similarities between hyperbolas and ellipses. HK is the center, so that will be the same as it was for an ellipse. A is still the distance from the center to a vertex. That hasn't changed. And C is still the distance from the center to a focus. But notice how now C is longer than A because the focus is farther from the center than the vertex. It was the opposite for an ellipse. The focus was between the center and the vertex. And so because of that, C is going to be calculated differently here. For hyperbolas, C squared is equal to A squared plus B squared. For ellipses, we had subtraction on the right side of that formula. So just be mindful of that. We didn't talk about the value b yet that we saw in the equation. We'll see where b comes into play here. Each branch of the hyperbola approaches two asymptotes. And let's kind of sketch out what that looks like. I didn't want to sketch it on the first picture because I had so many things labeled. I was out of space. But here's the center of the hyperbola. We're going to draw a rectangle here that has that as its center as well. So the center of the hyperbola is also the center of this rectangle. The length, in the horizontal case, the length of this rectangle is 2a. So half that length is a. And a is the distance from the center to a vertex. So there's one of our vertices. The other one's going to be over here because this distance is also a. And the height of this rectangle is 2b, so half that height is b. So that's where b comes from. And the asymptotes are going to be diagonals of this rectangle. So one of them is going to pass through this corner, through the center, and out the other corner. And then the other one will be on the opposite diagonal. And we already plotted our vertices, so then here's each branch of the hyperbola approaching that pair of asymptotes. So that's the horizontal case. We'll draw the vertical case over here. So for the vertical case, this distance is A and this distance is B because we're going to have our branches opening up and down. But the asymptotes are still diagonals of the rectangle. So when we say diagonal, we just mean the line that goes from one corner through the center to the opposite corner. Now if we want to write down the equations of these asymptotes, we can calculate the slope using A and B. So for the one we just drew, from the center to the corner here, we went up A and over B. So the slope there is A over B. And the two diagonals are going to intersect at the center, and the other one from the corner to the center would go down A over B. So it's the same slope except one's negative and one's positive. And then since they both pass through the center, that's a point on the line. And so we can use point slope form since we know the slope and a point. We'll practice that more when we're graphing in the next video. But I have it here for reference for you. Let's practice writing the equation. So here we have a hyperbola, and we have the branches opening to the left and to the right. So already we know that the x term is going to come first. So already we know it's going to look like this because the branches open left and right, except that should be subtraction because it's a hyperbola. All right, and we can see the center is right here at the origin because that's where the asymptotes are intersecting. So we actually have x minus 0 and y minus 0. So I'm just going to write these as x squared and y squared. The x squared term comes first because the branch is open left and right. So we've got our numerators set now that we found the center, and then we need to identify the values a and b. A is going to be a horizontal distance since the x term comes first. The distance from the center to the vertex is 3, and so a is 3, and this denominator is supposed to be a squared, so that's going to be 9. And then b is the distance from the center to the top of the rectangle, and that's a distance of 2, so b is 2, and this denominator is b squared, so that's 4. Here's a vertical example. We still have the center at the origin, the asymptotes intersect at the origin, so h and k are 0. This time the branches open up and down, so the y term is going to come first. And since it's centered at the origin, it's just y squared and x squared for the numerators. And now since we're in the vertical case, the vertical distance from the center to the top is a, and so that's 5. So a is 5, which means this denominator is 25 since it's a squared. And then the distance from the center to the right edge or the left edge, doesn't matter, is 3, so that's b. So b is 3, and so this denominator is 9.